Hi! In this Math from the Gut video, we're going to consider some possible lower limits for h, the length of the hypotenuse. In other words, can we find some lengths that are so low that the actual value of h is guaranteed to be larger or perhaps equal to that length? Believe it or not, what we're doing here is similar to what you'll later be doing in calculus and more advanced college-level math. So we start with a general triangle having lengths of x, y, and h. Is there some value that h must be longer then? You might want to pause and ponder on this a bit before continuing. One answer is so obvious that you might have missed it. Clearly, if we have an actual triangle, meaning that x and y are both greater than 0, then h must be greater than 0. In other words, our hypotenuse must have some length greater than 0. Now, let's test this idea out with the Pythagorean theorem. A lot of this will be a repeat of what we've already seen in part 3, where we consider degenerate cases where x and or y equaled 0. Therefore, I'll go through this quickly. We'll start with a completely degenerate case where x and y are both 0. In this case, we're not dealing with a triangle or even a line. We're just left with a point. As we've seen before, h is 0 as expected for this case. Now, we'll consider the partly degenerate case where only the x length or the y length, but not both, equal 0. Here, we're dealing with a line that is either in the x direction or the y direction. As we've seen in part 3, this means that h equals y when x is 0, or h equals x when y is 0. You can see here where we plugged in x equals 0, and here where we plugged in y equals 0. The important thing to note here is that both cases always give lengths greater than 0, since y is greater than 0 in the first case, and x is greater than 0 in the second case. So, in this case, the Pythagorean theorem is following our common sense idea that h must be greater than 0 when the length of either leg is greater than 0. Finally, we consider the normal triangle case where nothing is degenerate. In other words, where both legs have non-zero length. Starting with the Pythagorean theorem, we can see that this is greater than the square root of 0 squared plus 0 squared, since both x squared is greater than 0 squared, and y squared is greater than 0 squared, which means that the square root of x squared plus y squared is also greater than the square root of 0, or 0. So, to summarize everything, we see that, as we expect, h is greater than 0 if either x and or y is greater than 0. This means that the Pythagorean theorem passes our test of 0 being a lower limit. The only problem is that 0 is a pretty wimpy lower limit. In other words, can we find another lower limit that's bigger than 0 that h should also be larger than? If you haven't already figured this out, you might want to pause and ponder here. Okay, keep in mind that when we move along the hypotenuse, that we're doing two things at the same time. We're going over by a distance of x, and then up by a distance of y. Hopefully, it makes sense that doing both of these things at the same time requires traveling a longer distance than just going over or just going up. But if you're not convinced, we can revisit our picture from part 5 where we considered how h changes when x or y increases. But in this case, we're going to do the opposite and think about what happens to h as y gets smaller and heads towards a length of 0. So, this original triangle has a hypotenuse that we'll call h1. Watch what happens to it as we let the y length head towards 0. As we can see, and already know from part 3, this new hypotenuse, h2, now equals x. But, more importantly, we remember from our lake example in part 5 that points inside this blue circle are a shorter distance from the center of the circle than are points that are on the circle. Now, all points on the circle are a distance h1 from the center. But the point that is h2 from the center is inside the circle. This means that h1 is greater than h2. Since h2 and x are the same length, this also means that h1 is also greater than x. So, as y goes to 0, h gets smaller and heads towards a length of x. This means that our original h must always be longer than x, and that we can use x as a lower limit for h. Hopefully, you can now feel this in your gut. I'll leave it to you to picture the last example where x goes to 0 instead. Hopefully, you can see that h gets smaller and approaches a length of y. Therefore, y can also be used as a lower limit for h. Let's now see if the Pythagorean theorem obeys our common sense idea of x being a lower limit when we use a normal triangle that isn't degenerate. Starting with the Pythagorean theorem, we find that this length is greater than the square root of x squared plus 0 squared. This is because y squared is greater than 0 squared and causes the overall number under the square root sign to be larger. When the number under the square root sign is larger, then the overall number is also larger. You may remember that we discussed this in part 2. The number under the square root sign can be thought of as the area of a square, and that the square root can be thought of as that square's length. Therefore, when we increase the square's area, we also increase its length or square root. So, this means that the square root of x squared plus y squared is also larger than the square root of x squared, which equals x. This tells us that for all regular triangles, h is greater than x, and that x can be used as a lower limit. Also, if we had a degenerate triangle and y actually equals 0, then h would equal x, as we saw before. Hence, we can also say more generally that h is greater than or equal to x for all cases. In a completely similar way, we also see that h is greater than y for normal, non-degenerate triangles, and that h is greater than or equal to y for all cases. We can therefore say that the Pythagorean theorem also jives with the idea that x or y is a lower limit for h. I'm hoping that you can now look at the Pythagorean theorem and quickly see that this lower limit test is met. If not, I encourage you to spend a little more time thinking about it. Thanks for hanging in there. We just have one remaining test drive. For this one, we'll consider the opposite of what we've just done. In other words, upper limits. This time, we'll be searching for some number that is so large that h is guaranteed to be less than or perhaps equal to it. Please let me know if you're able to follow all of this. Am I going too fast or too slow? All ideas are very welcome and likely to get used in this or future videos. See you in part 8.